Have you ever been there, deep in a coding project, and suddenly you realize everything's just jammed into one giant main
Oh,
function?
yeah. It's like this sprawling jungle of code. Impossible to find anything.
Right. And trying to debug that, or worse, trying to get someone else to understand it.
Forget it.
Ugh.
It's slow, super inefficient, and yeah, debugging is an absolute nightmare. Looking for one tiny bug feels like searching for a needle in a haystack. A really, really big haystack.
This sounds painful. But thankfully, there's a much better way. And that's what we're diving into today. The elegance of C++ functions.
The heroes of structured programming.
Exactly. So our mission today is to really unpack functions, what kinds there are, how they actually work, the techniques that make them so crucial.
And we'll use a fun example along the way. Might involve some magical sports.
Looking forward to that. So functions, why bother? What's the big deal?
Well, it really boils down to a few key things. First up, modularity.
Breaking the code down.
Precisely. Into smaller, manageable, self-contained pieces. Think Legos. Each block does one specific thing.
Okay, and I guess that makes it easier for teams, right? Collaboration.
Absolutely.
Yeah.
If you've got these neat, separate blocks, different people can work on different functions at the same time without stepping on each other's toes,
Yeah, that makes sense. Less merge conflicts, faster development.
which leads directly to efficiency. You're just building things faster, more effectively. You're not wasting time untangling, spaghetti code.
And the big one, probably, maintainability.
Oh, huge. When something breaks or you need an update, so much easier to find the problem in a small function than wading through thousands of lines.
Fix it once, in one place. Okay, that makes a lot of sense.
Now, the interesting thing is you've likely been using functions all along, maybe without realizing it.
You mean the ones that come with C++?
Exactly. Predefined functions, they're ready-made tools.
Oh, like POW. For powers, like
Yeah.
POW 10-2 gives you 100.
Perfect example. And notice a few things about POW. It returns a value, right? 100. In this case, it's usually a double.
So it has a type.
It has a type because it gives you something back, and it takes values in, the 10 and the 2. Those are the parameters or arguments.
Right, the inputs.
And importantly, to use POW, you need that hashtag includes say math at the top.
Right.
That's the header file.
Got it. Header file tells the compiler about the function. Okay, so those are the built-in tools.
But what happens when the built-in tools aren't quite right? When you need something specific for your program.
Then we make our own.
Exactly. Roll up your sleeves time. User-defined functions. And there are basically two main kinds here.
Okay, what are they?
Value returning functions and void functions. Let's start with the value returning ones.
Value returning. The name kind of gives it away. They give you a value back.
Precisely. They do some work, calculate something, and then explicitly return one single value to wherever they were called from in your code.
So they need a type, just like POW.
Yes. They always have a data type declared int, double, string, whatever, specifying what kind of value is coming back.
In structure-wise.
They have a heading that's the data type, the function name, and the list of formal parameters, which are like placeholder variables.
Okay.
Then the body, which is the code that does the actual work, and inside that body, usually near the end, a return statement followed by the value to send back.
Right. So let's bring in the Quidditch. How would this work in our game?
Okay, imagine calculating scores. Let's say we have a function getSlytherin_number.
Okay.
When main calls it, maybe it passes in the number of regular goals Slytherin scored. That number is the actual parameter.
The real value.
The real value. Inside getSlytherin_number, that value gets copied into its formal parameter. Let's call it numGoals.
The placeholder.
Right. The function then multiplies numGoals by, say, 10 points for a regular goal. It calculates the total.
And then?
And then it returns that total, just the number. That number goes back to main, maybe gets stored in a variable like total score Slytherin.
Got it. So main calls it with a number, the function does its math, and sends one number back. Clear.
Perfect example of value returning.
Okay, so what about the other kind? Void functions. They sound empty.
Huh. Well, they don't return a value. That's the key difference. They do not have a data type in their heading because nothing comes back.
So if they don't return anything, what's the point? What do?
They perform actions, they do things, print something to the screen, modify a file, maybe update something, but they don't send a result back using return.
Okay, so a call to a void function isn't part of an equation or assignment?
Exactly. It's a standalone statement. Just do something on its own line. You can't say X do something because do something doesn't give you a value for X.
Right. So people might think they're less useful because they don't return stuff? Is that a common trip up?
It can be, yeah. People sometimes think if it doesn't return, it can't affect anything outside itself. But that's not quite right. They perform actions, and crucially, how we get information into them, or sometimes let them influence things outside. That's where parameter passing comes in again.
Ah, okay. So how do we pass parameters to these void functions?
Two main ways, similar to value returning, but with a twist. First, value parameters.
Same idea as before, passing a copy.
Exactly the same.
Hmm.
The value from the actual parameter, in main, say, is copied into the formal parameter inside the function.
And crucially, it's a one-way street. The function can't change the original variable back in main.
Correct. It get the copy, works with the copy,
Mm-hmm.
but the original is untouched. Think about our Quidditch game again, maybe a print-gen function.
Okay.
It might take the total score Slytherin and total score Gryffindor as value parameters. It uses those scores inside to print, Gryffindor wins or whatever.
But it doesn't change the actual scores themselves.
Nope. It just uses the values it received to perform its action, the printing. Nothing gets pushed back out to the original score variables.
Okay, standard input via copies. But you said there was a twist with void functions?
Yes. This is where it gets really interesting. The second way, reference parameters.
Reference. Sounds like it refers back to something.
Exactly. This is the big exception for void functions. They can effectively pass information back out, or rather, they can change the original variable.
How? If there's no return?
Because instead of passing a copy of the value, you pass the memory location, the address of the actual parameter.
Whoa. So the parameter inside the function and the original variable outside, they're pointing to the same place in memory.
Precisely. They share the same memory address. It's like giving the function the actual key to the variable's house, not just a photo of it.
So if the function changes its parameter...
It's directly changing the original variable back where it was called from.
Yeah.
Instantly, because they're linked.
Okay, that sounds powerful and potentially dangerous. Let's see it in the Quidditch game.
Okay, picture this. Malfoy decides to interfere. We have a Malfoycent function.
Uh-oh.
And when we define it, we use an ampersand next to the parameter type, like void Malfoycent and total score. That ampersand signals a reference parameter.
In total score, okay.
Now, inside this function, Malfoy casts Confondo. Let's say the spell adds 100 points to total scoresly.
So inside the function, that parameter total scoresly increases by 100.
Yes. And because it's a reference parameter linked to the original total score Slytherin variable back in, say, our global scope.
The actual total score Slytherin variable instantly jumps up by 100 points, even though the function is void and didn't return anything.
Exactly. If Slytherin had 50 points, suddenly, poof, they have 150. The game state is radically altered from within that void function.
Wow. So Harry sees this happen.
He does. And he has to react. Because Malfoy cheated, Harry might need to, say, cast his chant spell multiple times, maybe an Agua Mentis spell to counter it. Perhaps he has to cast it like 14 extra times just to tie the score before catching the snitch.
Making his voice almost give out.
Right. All because that reference parameter allowed Malfoy's function to directly change the game's reality. It shows the immediate, powerful impact. Final score, Gryffindor 300, Slytherin 150.
It's a fantastic illustration of the difference. Reference parameters let void functions have a direct modifying effect outside themselves. Huge concept.
Absolutely fundamental.
Okay, so we've got predefined, user-defined, value returning, void, value parameters, reference parameters. Let's zoom out a bit. How do these pieces fit together in a bigger program? Let's talk scope.
Right. Scope is all about where things are visible or accessible. Where can you use a certain variable or function name?
You mentioned global variables earlier.
Yeah, global variables,
Mm-hmm.
defined before main. They're accessible pretty much anywhere in your program file. Top-level visibility.
And then inside functions.
Those are local variables. Defined inside a function block, they're only accessible within that specific function or block. They live and die there.
Now, you mentioned total score Slytherin might be global, and we just saw a function changing it via a reference parameter. That sounds risky.
It is risky. This is a major ouch moment. Using reference parameters to modify global variables can make your code incredibly hard to debug.
Why? Because the change could come from anywhere.
Exactly. If multiple functions can all directly change the same global variable, and something goes wrong, trying to trace which function caused the error becomes a nightmare. It breaks that nice modularity we talked about.
Creates hidden dependencies, side effects.
All of that. It compromises predictability. That's why developers try to limit shared, mutable state global variables that can be changed from many places. Global constants, though, are usually fine because their value doesn't change.
So minimize modifiable globals, especially with reference parameters. What if you have a local variable with the same name as a global one?
Ah, inside the function, the local variable takes precedence. But if you really need to access the global one with the same name from within that function, you can use the scope resolution operator, the double colon par. So, my global var. Often yes. Good naming avoids that confusion.
All right. What about organizing the code itself? I've seen main sometimes appear near the top, sometimes near the bottom, with functions defined before it.
Yeah, that relates to how C++ compilers work. They read your code top-down.
So if main calls a function domagic, that's defined later in the file.
The compiler gets to the call in main and says, wait, what's domagic? I haven't seen that yet. Error.
But defining all your functions before main can make the file feel upside down, right? You want main to show the main flow early.
That's the common preference.
Yeah.
And the solution is function prototypes.
Prototypes, like a blueprint.
Exactly like a blueprint. It's a declaration, usually placed before main, often near includes and global variables. It tells the compiler the function's return type, name, and its formal parameter list, basically, its signature.
But not the function's body, not the
Yeah.
actual code.
Correct, just the heading, followed by a semicolon, like int calculus score, int goals, int smidge. It tells the compiler, hey, a function like this exists. Trust me, you'll find the full definition later.
So you can put the prototype before main, satisfying the compiler, and then put the full function definition after main, keeping your code nicely organized.
Precisely. Cleaner structure, happy compiler.
Makes sense. One last concept you mentioned, function overloading.
Right. This is a neat feature. Overloading means you can have multiple functions with the exact same name.
Wait, how does that work? How does C++ know which one to call?
The key is they must have a different formal parameter list. Either the number of parameters is different, or the data types of the parameters are different, or both.
Ah, so the name plus the parameter list that's unique.
That combination is called the function signature. The compiler looks at the arguments you provide when you call the function and matches them to the signature of one of the overloaded functions.
So you could have print result and print score and print result, string message, both named print result, and the compiler figures it out based on whether you pass an integer or a string.
Exactly. It allows you to create more intuitive function names that can handle slightly different kinds of input gracefully. It's flexible. Just a quick intro to it today, though.
Got it. Wow, okay, that was a serious deep dive. We went from that tangled mess of a single main function.
To seeing how functions create order. Modularity, easier collaboration, more efficient development, and much better maintainability.
We looked at the ready-made predefined functions and then crafted our own user-defined ones, the value returning type that gives back a single result.
And the void functions that perform actions. And within void functions, the crucial difference between value parameters, passing copies.
And those powerful reference parameters, the ones that use memory addresses to let functions directly change variables outside their own scope. That Malfoy example really drove that home.
Definitely a key takeaway. Plus, we covered scope global versus local and the caution about globals with reference parameters.
And how function prototypes help us organize our code cleanly, letting us define functions after main. And finally, a glimpse of function overloading, same name, different parameters.
It's all about building blocks and how they interact.
And really, understanding all this isn't just about C++ syntax. It feels like it gives you, the listener, a shortcut to thinking like a software architect, not just a coder. Moving from just writing lines to designing systems that are robust, scalable, easy to work on.
Absolutely. It's about building better software, fundamentally.
So, to leave you with something to think about, we saw how reference parameters directly manipulate memory locations. How might a deeper understanding of that, of memory management in general, influence how you think about designing programs for security and efficiency in the future?
Something to chew on. It connects function design directly to lower-level system behavior.